Okay, hello everybody. Is my microphone working? I'm going to need my microphone. I'm losing my voice. So, welcome to the Physics Magic Show. We're not allowed to call it the Physics Magic Show because Open Day is serious this year. And so we call it the Magic and Mystery of Physics. But internally we're all smashed. This is David Cooks, this is Varun, I can't pronounce your surname, this is Helen Pass. These are real members of the physics department, so we laser physics, Varun is lasers and biophotonics, and we're all terribly serious, and this is a nice thing for us to get to do. So we're going to show you some demos. None of what we're going to show you is magic. This is not a magic show. We're going to tell you how we do it, because all of these are physics tricks. So it's nice to see something that's impressive and then be told how to do it, how we do it as well. So, we were supposed to have 3 hours to set up and we got 15 minutes, so this is why chaos, okay? Okay, so, first thing we're going to do is, can you get these out of the way, please?
Where should I put them?
Put wherever you like.
In the box. Is that alright if I put them in the box?
Okay, perfect. Right, water everywhere, perfect. This could be a great physics trick. Okay, so we're going to talk about a few different things. First thing we're going to talk about is we're going to do some demos to do with sound and waves. So you saw the wine music on the videos. Here's a wine glass. That's the first note that he played. I can't do any of the others. Waves are vibrations. So when this wine glass gets hit, it vibrates. Actually what it's doing is the ring of the lip of the wine glass is deforming one way, then the other. That makes the air around it vibrate. The vibrating air moves to you and you hear it in your ears. That's all that's happening. So when I excite this, it makes sound. But I can also do the opposite. I can excite it using sound. So what I'm going to do is I'm going to use this guy here. This is a fancy speaker. What are you doing?
Put the balloons away like you said in this box.
Okay, so I'm going to use sound to excite the wine glass, and if you excite it hard enough, it vibrates so much it's going to smash, and it's going to be terribly impressive. I'm going to use this expensive piece of electronics to do it, which is an iPhone.
Don't forget his safety glasses.
Hey?
Don't forget safety glasses.
Oh, we can't have... He's got safety glasses. Okay, so... that's wrong. Everything is wrong. Oh, thank you. So, I'm going to make a mediumly quiet sound. So now the wine glass is shaking around quite a lot. My straw keeps moving. Now if I turn it up enough, what's going to happen now is that the whole wine glass is going to shake so much that it's going to break. It's going to be quite loud, but not desperately loud, sort of like a Miley Cyrus concert, but more musical. If you want to block your ears, that's fine, but it's not going to be super loud, okay? Ready? Watch the wine glass, and so hopefully something will happen. Ready? That's a terrifying demo, because if it doesn't work, what do you do? Okay. There's plenty of other ways of making sounds, and we've got a few of them. Helen is an expert at making sound. That's just a steel rod. Helen's one of the only people in the department that can do this.
That is aluminium. This is stainless steel.
This is actually the whole rod getting longer and shorter and longer and shorter. And that makes the air vibrate. You can hear it.
Use a bigger one, Helen. That's too small.
Big.
Use a bigger one.
Bigger rod. Bigger rod. Come on.
You've got to find the middle, because the whole rod is shaking, except at the middle.
Oh, that's really good, Helen. Oh,
Wrong end. That had sticky tape on it. Never say never.
it's like a violin. You need the right equipment. You need rosin on your fingers.
A little bit of rosin to make it sticky. I only found this one this morning.
Yay! Okay, any vibrating things will make sound. You can do it with these pipes. That was impressive. So these things are
You can do it with a balloon.
these things are terribly confusing. These things make sound. If you go faster, they make a different sound. That's actually a harmonic. So everything that vibrates has harmonics. Bugles don't have any keys on them, but you can make lots of different notes out of them. All the harmonics. It's the same set of notes that you get out of this pipe. That sounds like a bugle. Why it makes noise is really complicated. You can use straws.
Oh, straws.
We got straws too. You can make music with straws.
So you can't do all these tricks at home, but here's one that you can certainly do at home, or you can try. So I do have one that I prepared earlier. Flatten the end of the straw with your teeth. Cut it to quite a sharp point. Whoops. And scissors. Let's see. I don't know if it's going to work or not.
It's got to work, Helen. It's got to work.
This is a professor's party trick.
This is why physicists don't
Here's one that I prepared earlier. You know, the scissors punch the end.
Can you do it when you're laughing?
Okay. Alright. Right, we're going to make some waves on water now.
We're about the pipes, Dave.
Pipes. We're going to make noises with pipes. Helen's got a pipe over here, and she's going to make noise with the pipe.
I've got this. This is a bit bigger than a straw, isn't it? Isn't this big?
Okay. Don't try this one at home. Set party guttering.
Nothing in it.
Oh.
It's really only a little pipe. Who wants a bigger pipe? Big pipe! Big pipe!
Oh, it's coming. Big pipe. Big pipe. Big pipe. Big pipe. Big pipe.
This is a bigger pipe.
What's that? Okay, that's another vibrating, it's just everything vibrates. That's a vibrating air column, so it's the column of air inside the pipe just being excited. That excites the air, you hear it. Okay, Helen's keeping me on track with the schedule. Right, we're going to make some waves with water. And we're going to do this with the lights off, and we're going to try not to flood the lecture theatre, which probably will happen. Especially if I set the lights off.
Did you wash your face this morning, Varun?
Okay, so that's pretty good. Can you pull the cork through? That's so cool. So what we're doing here is with water's coming out of the pipe, the end of the pipe here is being vibrated up and down a little bit. And it looks like the water's... So it looks like the water's doing something crazy. Clearly the water's not doing that. So we're using the strobe lighting to make it look like it is. What the water's actually doing, Helen can show us in slow motion, but the water's not doing that. The water's coming out like this, but a lot faster. And what we're doing with the strobe is that the pipe at the end here is vibrating up and... The pipe at the end is vibrating up and down about 20 times a second. If we flash the light exactly at the same 20 times a second, whenever it gets lit up, you see exactly the same pattern of water. So it seems to be frozen. It's not frozen, of course, it's moving, and it's blurry when we have the lights on. But with the strobe light, we can freeze it, we can make it go forwards, we can make it go backwards, which is quite disconcerting. And you can do this with any repetitive motion. So sometimes you see sometimes when you see helicopters or car wheels on TV, you see a similar strobing effect. Okay. That was... So this is what it's doing under real light, see? So it's just completely blurred. Okay. Okay, we haven't set fire to anything or flooded anything. Or tripped the fuses yet. Okay, onwards. Okay, so sound is a wave. That was a water wave. The other thing this wave is light. Light is a wave. Light's an electromagnetic wave. So we're going to do some light demos. These things are laser dyes. So a laser dye is something that takes energy from somewhere. In this case, it takes energy from a UV lamp. See, these are quite dull normally. This is just UV light. The laser dyes take in the UV light, they store it, and they emit it at their own preferred wavelengths. To do that, you need an energy source. There's other ways of getting energy sources. We're going to show you fluorescent light tubes. Oh, that's fluorescent light tubes. So this is a fluorescent light tube getting power from electromagnetic waves in the air.
Yeah, that's a little tube.
Okay. So that's probably going to blow up the console. Okay, so that's the light getting energy from electromagnetic fields. That's the Tesla port, by the way, this thing. You can see, you can make much bigger ones of these. This is the dyes getting energy from the ultraviolet light. To make a laser, you take a material that can do this, and you give it energy, and you give it some mirrors, and David is going to show me his lasers.
Maybe you can do this.
I can do that, yeah. So everyone knows lasers.
Little laser pointers.
Lasers are a very specific colour, and the light all goes in the same direction.
We've got some steam already.
And you can see the beam.
There's something suspicious going on down here. I don't know that. So you normally can't see the beams because all the photons are going in the same direction. None of them come to you. But if we scatter the photons, the light, using this is talcum powder, so my hands are going to be lovely soft later. You can see the beams propagating in the air. What? Oh.
They put it just, yeah, that's the way. All over the floor.
So different colour lasers, different laser materials. Oh my goodness, I've lost now. It's so dark. What's next? Oh, is it?
Lights.
So that was sound and waves. So now I'm just going to tell you a few things that sound and waves are useful for. This is a plane going faster than Mach 1. Faster than the speed of sound, you get a sonic boom. This is Concorde.
She's rocking. There's the smoke.
Concorde doesn't fly anymore, unfortunately, but Concorde was the only passenger jet to go faster than the speed of sound. The swept-back wings are all to do with managing the forces that you get when you go faster than the speed of sound. You get shock waves. Very pretty. Not so pretty when it was on fire. This is ultrasound. So ultrasound looks inside things like pregnant ladies with ultrasonic sound waves. It reflects off boundaries between different densities of material, and you can see the difference between those materials. Radio waves. Radio waves are everywhere. We use radio waves for receiving radio, but we also use microwaves for receiving phone calls. That's why we have all these towers over the place.
The world's largest solar panel power plant is now
Capturing waves is really important these days. So solar power is about capturing electromagnetic waves, which is light, and turning them to electricity. Astronomers love lasers. You actually fire a laser out of a telescope. The laser makes an artificial star high up in the atmosphere, and by looking at that star, you can correct for the twinkling of the atmosphere. Okay, we are done with sound and waves. Are we saving on time? No. Okay, we're going to do some magnetism demos. These are my magnetism demos. Let's have some more lights. Lights. Okay. So, magnets do all sorts of strange things. We all know that magnets attract other magnets, and magnets repel other magnets, but that's not super interesting. What I'm interested in is magnets making power. So, this is actually just a coil of wire, and this is a meter that tells me what current is flowing through the wire. This is just a magnet, it's quite a big magnet, and I'm going to be careful not to get it trapped on any metal. If I move it near the coil, I generate current. So the wire's not magnetic. What's happening is the magnetic field moving near the current carrying wire generates current. This is the basis for the vast majority of power generation. So, what am I going to do next? Oops. I meant to do that. Yeah, I made it look easy. Okay, so moving magnets create currents. Moving conductors create currents as well. So here's a swinging circle. What are you doing? We could do it that way. It'd be even better to do this way, couldn't it? Okay, so you see this swings for a long time? If I put a magnet in here, it's swinging through the magnet, it's not touching the magnet, and this is not magnetic, so it doesn't get attracted to or repelled to the magnet. But even so, it gets stopped. And the reason it gets stopped is as it goes through the magnetic field, currents get generated in the copper, and those currents dissipate power, and it slows it down. It's much better if I cool it down. Can I borrow some liquid nitrogen? Oh, we've got some of that one. So if I cool copper down with liquid nitrogen, liquid nitrogen is 70 Kelvin, so minus 200 and something centigrade. All sorts of uses, like storage. Copper gets to be a much better conductor when you cool it down. So if I cool down the copper as well. If I cool this down, it's a better conductor and it does this trick better. And I've probably got it too hot now. Disappointing. That was slightly slower. It's falling. Got hot quick. So when it gets super cold, it suddenly stops. Quite impressive. So this is all to do with, this is magnetic induction, we call it, but you might see it as magnetic braking. And we know why we use this. We'll show you why you use this in out in the real world. This is another piece of copper. This is a copper ramp. This is not a magnet. This is just a piece of metal. Pretty much as expected. This is a magnet. Trying to hurt himself. That doesn't want to go down the hill because as it rolls, the magnet is moving next to the copper. The copper stops it from moving. Go. Okay. So that's again, it's magnetic. Oh, ouch.
That's magic.
That is quite magic. I nearly lost my fingers again. Okay, this is a big piece of copper. This is a big piece of copper, which we've cooled in liquid nitrogen, so it's pretty cold. I know this thing looks like it was built in a garage, and it was. I built it in my garage yesterday. My daughter liked that. You helped, didn't you? And this does the same thing. So the copper is not magnetic, so the magnet doesn't stick to it. But if I try and move it, it's really hard to move the magnet. And if I drop it, it doesn't want to hit it. If it was even colder, it would be even better. So as it moves towards the disk, as soon as it gets close, magnetic braking slows it right down, and it kind of bounces off before it even hits it. Are you going to put it on its side? So that's all magnetic braking. The other thing you can do with magnets is levitation. This braking effect is to do with the fact that the copper is a conductor. So if you use something which is a superconductor, the braking effect gets perfect. So if I put a superconductor over my copper, if I put a superconductor over my magnet, it levitates because it can't drop. Its braking is perfect. So what this is a little piece of superconductor, which we call the liquid nitrogen, and that's going to levitate above these magnets. So that's magnetic levitation, don't lose it. And it will do that as long as the superconductor stays cold enough. That superconductor, I don't know what it is actually, but as it warms up, it will start to be a conductor, and then the perfect braking goes away. Ah, it's fallen. Oh no! Always wear gloves when dealing with liquid nitrogen. And don't wander around with magnets because you'll end up in trouble. Okay. We're doing quite well. You don't do it. Pens? Yes, cans. Okay, no. Magnetism. So I'll show you some magnetism. Moving magnets create currents. That's how we generate power. This is a power generating turbine, which is a load of magnets which get spun and they generate currents in power stations. This is magnetic resonance imaging. So this uses magnetic resonance with water normally, and we use it to look inside people's heads. This is somebody's brain. Not very nice.
The fastest passenger train in the world has broken its own speed record during
magnetic
a test run.
levitation. This is a magnetically levitating train. This is a hard drive. Hard drives are magnetic. They store information in magnetic fields. And they move incredibly quickly. This is 40 times slowed down. It's a little reed head moving across the surface of a hard disk. Really impressive technology, maybe getting phased out these days, but it's done good for a long time. Magnetic braking in cars. You slow the car down using magnetic braking effects like we've seen here, store the energy, and then use it later to drive an electric motor to make you go faster. And slightly less exciting, this is a commercial car. This technology is coming into mainstream cars now. So you slow yourself down by magnetic braking, store the energy, reuse it later, so you don't waste the energy when you brake. Right, so that was magnets. We're back. So, now we're going to talk about fluids. Physicists are a little bit odd. When you hear fluids, you probably think liquids. but for physicists, fluids includes gases. So fluids are something that fills the space. Air is a fluid. And air is pretty heavy. A cubic meter of air is about a kilogram, actually. It's just surprising, a cubic meter of air. Thank you very much. He's terribly serious in the week. It's amazing.
I'm putting my balloons away, as you said.
What are you doing?
I'm putting these balloons away, just like you said.
How many have you got?
How many have I put in there? Who's been counting? I forgot to get someone to count. How many are in there so far? Just one. We'll see at the end.
Cubic meter of air is a kilogram. And there's a lot of air above us, and all that air is pushing down. What that means is the air down here on the surface of the Earth is really compressed and is at a high pressure. And the air down here pushes against everything with a force of about a kilogram per square centimetre. So every surface sideways, every surface upwards is being pushed on kilogram per square centimetre. Might not sound much, but a kilogram per square centimetre adds up. This Coke can's got a surface area of about, shouldn't have thought about that. I don't know, 100 square centimetres, something like that. So 100 kilos are pushing on the outside of this Coke can. It doesn't care, because there's air inside as well, and that pushes out with the same force. What we're going to do is, we are going to get rid of the air from the Coke can. The way we're going to do it is we're going to replace it with steam. So I'll put a little bit of water in here. I'm going to heat it up, and the water's going to start to boil. And the boiling water creates steam. The steam fills the can up and it pushes all the air out. So what I'm trying to do is I'm trying to fill the can with steam. Then what I'm going to do is I'm going to flip it upside down here. And as the steam cools, condenses into water, which takes up a tiny bit of space, all of a sudden I've got 100 kilos crushing my can, and it really does mind then.
Dave, that was such a little pen. Haven't you got a bigger can? Big can! You got a bigger can?
Yeah, go for it. So here's the bigger can. So this has been sitting down here and it's been boiling, so hopefully it's full of steam. And we're going to cool it down.
Inside?
Yeah, inside. And inside. That was faster than last year. So this can is huge. This can has got a surface area about 10 times more. So there's a ton of force compressing that can from the outside. This was a pretty tough can. We paid a lot of money for it.
This can, come on.
Yeah, that was $30, Mike. Sorry. So that's what air pressure can do to you.
You got air, haven't you?
I've got big balloon for you, Dave.
You want a bigger balloon?
Yeah.
All right, then I'll work on a bigger balloon. Is it going to fit? Fine. We'll see.
It's not going to fit.
Probably not.
Okay. Okay, last trick. Last trick is the runs. Go on, Dave, push on. Last trick is Varun's toy here. This is my favourite. This is secret. It's got a clock on. Just to build excitement. Please don't look at the logo. It's the wrong logo.
This is the magic act. Look, so you're going to cut in half.
So what have you got in there, Varun? Show us. Yay! That's pretty cool. So it's a box full of nothing. No, it's not full of nothing. It's full of gas. What sort of gas? It's not full of air.
Wow.
So this is a box full of something called SF6. SF6 is a gas, but it's a very heavy gas, and I've forgotten how heavy it is. But it's about 10 times heavier than air. And so we normally think of gases as filling spaces, but SF6 doesn't. SF6 sits at the bottom of the container, just like water would sit at the bottom of the container. This is dry ice in water. Dry ice is solid carbon dioxide, and it boils to give you carbon dioxide gas. But because the carbon dioxide is cold, it condenses water vapor out of the air, which is why you get clouds. So the SF6 sits in the bottom of the container, and just like you can float a boat in water, you can float a boat in SF6. You don't have to have a liquid, you just have to have a heavier fluid beneath the lighter fluid. You can float a boat on the border. You can sink the boat by taking the invisible gas in a container and pouring it into the boat. Come on, get down there. It's unsinkable. It's the Titanic.
I made it a bit too well.
Your boat is too good, but it is going down.
Oh, wait, faster.
Whoops. Don't pour it that much. How is that not sinking? That's magic. I don't know why that's not sinking. Okay, it is the unsinkable boat. Is it supposed to float?
There you go.
Yes!
Yes!
That's a better place to store the balloons.
Do we have a minion to move forward?
Did the minion go in?
For the minion? I just put the minion away.
So,
Is it time to get the minion back out?
it is.
I reckon.
So, the balloons, David's box is full of liquid nitrogen, you may have guessed. Putting the balloons in the liquid nitrogen is the same trick as the Coke cans and the cans. When you put the balloons into liquid nitrogen, they get cold. The air gets cold, and the air takes up less space when it's cold. Actually, the air liquefies inside the balloon, which is quite cool. Bring them out again, they heat up, and they'll start to expand. Oh, we look so sad. Keep going up. Come on, come on. You need these. There we go. He's going there. There we go. Oh, we did so well. Okay, so that was a little about fluids. Fluids in the real world. Hot air balloons float because the hot air inside them takes up less, weighs less than the cold air outside. You guys are so noisy. Submarines have to take huge pressures, so you don't design them like this. Submarines look like spheres normally, or elongated spheres like eggs, so they can take the pressure. Go down 10 meters in the water, the pressure is double what it is on the surface. Fluids. Very hot gases thrown out the back of a rocket give you a force equal and opposite forwards, which is how they take off. Aerodynamics. How do objects interact with fluids? This is how you take off in a crosswind. It's a so-called aerodynamics is all about how the wings give you. And cars and racing cars use aerodynamics to give you downforce. Wind turbines use moving wind to give you forces on blades to give you rotation. And that rotation moves magnets which generates power. Okay, I think we've about run out, and it's actually not gone too badly considering. We're terribly serious. We actually do proper physics. If you come and do some undergraduate courses, then you learn exactly why all of this happens. Feel free to come ask us questions afterwards. We also have hands-on physics, which is down in the far bottom left corner of the building. So go and play with some things like this, have some fun. Thank you very much.